Okay. Um, I think we can get started. I hopefully more kids join as we get on. I know that's happened a lot before, but let's get right to it. Okay, so for today, Gavin's gonna be our TA. So if you guys have any questions, you can just feel free to ask Gavin. He is more than willing to help. But and then sorry, let me just get my uh Gavin, are you able to make my iPad co-host?
I'm not the host of this.
Oh, so you can't even
Yeah, I think it's just shut in.
but you can't make me
Oh
co-host either.
wait,
Try making my iPad co-host. It's not letting it's like
okay.
my thing's lagging. I made you co-host, that's what.
No,
Okay.
I can't. I can't.
Ah, you can't. All right, then it's fine. It
Okay.
should be it doesn't matter. All right. Um, sorry, I don't know why it says kinematics. Okay, welcome to Intro to Physics again. It's just I'm gonna be the tutor for today, and then yeah, we just started. Don't worry. Um, oh yeah, Gavin, do you actually let me link the Google Classroom attendance in the chat really quick so you guys can fill that out. But if you guys have any questions, feel free to ask Gavin because I'm gonna be teaching for a lot of the time and I won't be able to see your guys' questions and I don't wanna I want your questions to be answered. So oh okay, good. A lot of you already turned it in, but I'll just put it in chat again. Uh yeah, I put it in chat. Let's and then can you admit people, Gavin, or no?
Yeah, yeah, I can.
Okay. Okay. Sorry about that, guys. Okay. Yeah, welcome to Intro to Physics. This is class 7. Today we're going to be covering a lot with Atwood machines and like rotational kinematics. That'll be our two main topics, and then we'll have like many topics like pressure and then Young's modulus. But those are just like fun concepts that we'll learn. So first, the first thing we're going to learn about is pressure, and basically pressure is just the force applied to a certain area. And I feel like that should make quite a bit of just sense logically because if you think about it, like I don't like this example here, but if you take like a board, like a wooden plank, and you apply some force over all of this area, that's like pressure, right? Like that's the amount of pressure you're putting. So I think that's a really great way to look at it. There's not much to the slide, but I think just conceptually, that's a good way to think about pressure. And pressure is measured in pascals. Okay. So whenever you think of pressure, just think of pascals. And yeah, 1 pascal equals 1 Newton per meter squared. That's pretty logical because we know force is equal to newtons. And then it's just area, like the area of the shape. You know how a square has like meters squared as the area? Or whatever lengthwise unit you have. So for pascals, it's just 1 pascal equals Newton per meter squared. And then this is all dimensional analysis. I do this to get you guys like looking at dimensional analysis. Like, and that's just basically just looking at the units. It's a fancy name, but I'm just saying looking at the units given for each question, right? Um, so when we're looking at other common units, there's atmospheres, core, bar, PSI. There's a lot of different other units for Pascal as well. This is a fun fact. 1 atmosphere is equal to 101,325 pascals. And in liquids, the pressure is equal to the density times gravity times the height, right? Or the depth of the thing, right? So if you ever see this P, it's just going to be the density of the fluid. And then you have gravity, which is 10 meters per second squared. And then you have the height, which is also meters, right? So, yeah, as you can see, pressure increases with depth because there's more water overall being applied downwards. Um, I think that makes pretty much sense. Like that makes sense. I don't know if you guys have any questions, just feel free to pop in chat. Um, we'll do some questions with pressure today if we have time at the end of class, but or maybe next time. But that's just a quick overview of pressure. Do you guys have any questions about pressure? No. Okay. Moving on to Young's modulus. This kind of goes well with pressure because that's why I kind of mentioned it, is because it talks about how much a material stretches or compresses under stress. If we have time at the end of class, I'll put a booket on, but if we go until then there won't be a booket like Lucas did last time, right? So if you look at Young's modulus, it's just basically it's a really fancy name for just stating that it's just talking about material stiffness for an object, right? So the equation for Young's modulus is just stress over strain, right? And another word for stress is just, oh, sorry. Another word for stress, what the heck? Sorry, okay, there we go. Another word for stress is just pressure, right? If you look at stress, you can see that stress has the same equation as pressure, F over A. So you can tell that um it'll be the same exact thing. And then strain is just basically looking at like strain is talking about like the like how much like the proportion, the ratio of the length of the object, right? So if we're talking about stress, it's we're talking about how much pressure is being applied, and then strain is talking about how much it's moving, right? So we can see that this is I don't know if you guys will understand it better with the picture, but it's like it's almost like elasticity. It's just like a quick overview. I don't expect you guys to know Young's modulus or like understand it at all completely, but um do we need to copy what each variable is? No, because this is like maybe for the next topics, but for right now, this is just a quick overview of pressure and Young's modulus just to get class started, just to get your minds warmed up. But if you want to, you can. I would be more than happy if you did. But okay, just a quick warm up for today's class about pressure and Young's modulus. Is there any questions, or can I move on? We should have covered this last class, but I just wanted to get a quick because last class we talked about the four fundamental forces. I think this would tie in really well with the four fundamental forces. But and just really quickly talking about force fields. A force field is basically a region of space where like an object experiences some type of force without contact, right? We talked about non-contact forces with Lucas as well. It's just basically a non-contact force, right? Have you heard of like a magnetic force field? Like if you take two magnetics with magnets, sorry, if you take two magnets, one north and one south, each of these has like a Each of these has, sorry, wait, I'm doing this wrong. Each of these has a magnetic force field that gets applied to each side, and that's why if you do something like this, these will repel without ever touching. While if you have them opposite with the north and south, then they'll attract because these arrows will be well, because these arrows, if it was the other way, would be pointing towards each other. And I think I didn't draw it very well, but I think this picture does a really good job of showing how these arrows kind of interact with each other, right? And that's kind of how yeah, that's how kind of like how have you seen those magnetic like bullet trains that like kind of they're kind of floating over the train tracks? That's because what's happening is if there's this train right here, right? If they have this train, there's magnets on this train and on this track, right? And what this track is doing is it's switching its let's say this is north and this is north, right? And let's say this is south and south, right? It's gonna switch these fields like really quickly every single time. So it just keeps on repelling and it just this train moves forward, right? That's basically what trains do to like that's how they use the magnets to kind of move forward. That's like a really simplified version. It's a lot more complicated than that, but that's just a really simplified version of how force fields would like a real life example would work. It's kind of like a propeller. It's almost like a propeller, but like it's using forces to so basically like if you let's say you have two magnets like yeah, let's say you have two magnets like I'm pretty sure this is how it works, but let's say you have two magnets like this, north and south, and then you have north and south right above each other, right? Basically this north will want to go here, and let's say there's another magnet right here, right? And there's just this is the train track. Let's say this is the train track, this is the train. This north will want to go here, and this south will want to go here, right? And then it'll just switch. So then once it goes here, stopping, that's a good question. How would it stop? I don't know too much about the magnetic trains, but I know that's what they kind of do to have it. And then I'm assuming they switch it through that's how they use so basically there's something called electromagnetic forces, and basically they do that through electricity. They switch it through electricity with like and they don't use real magnets, right? They just this I'm using the example of magnets as a really simplified version. They do this with electromagnetism electromagnetism, and that's yeah, like that's yeah, and that's how they switch it. Stopping is a good question. I'm assuming that they have something with the magnets that have it stop. But that's just a really simplified version. I don't know too much about it, but I've worked with electromagnetism a bit with physics and bullet trains. But another field is the gravitational field. As you can tell, gravity is not a non-contact force. It's just a force that pulls down. Yeah, it's like the non-simplified version goes into like not quantum mechanics, but it goes like really in depth into I think I can pull up a picture actually. Let's see if I can pull up a picture. Magnetic. I'm curious now. Sorry. Magnetic trains physics on track. Let's see if that works. Yeah, okay, this is what I was talking about, right? You see how I drew the picture? This is what I was talking about. This is actually a really good picture. Um, but if you look at it, this goes here and you can kind of see how yeah, it is expensive. That's why you don't see too much of him. but it's like worth it because it saves a lot of it goes faster, it's more efficient, and but it is really expensive because it does use superconducting magnets, and working with superconductivity takes a lot of is the sorry, I didn't check. It's the four fundamental. Yeah. The four fundamental, sorry, if you guys weren't here for last class, the four fundamental forces are gravity, electromagnetism, strong nuclear force, and weak nuclear force. So the force that's being acted upon here is the electromagnetism, right? Does this picture I think this picture does a lot of justice. Can you show I don't think I can show with simple math. It would take a lot of it would take more it would take a lot of higher math to do, but um I can try to find other pictures. Yeah. This is another good picture. This is basically these are all really simplified versions of how it works. But I want to see the brake system. Brake system. I'm assuming they just have it stop through. Okay, I would have to look into it further, but I hope that picture kind of the pictures before kind of shows what I was saying with the annotations a bit better. The math would be a lot more complicated, but it's a lot more environmental friendly. It's a lot more because it's using electricity. It's not using gas at all. And it's like if you think about it, you're just using magnets, right? Magnets is a force in itself. And if you think about it, that doesn't take any like if you put two magnets towards each other and they repel, it's not using energy, but except for the forces, right? You're not using like gasoline or like electricity to move those magnets apart, correct? So it's a lot more environmental friendly. It's just really expensive. That's why you don't see it in a lot of places yet. Japan, they have a lot of it, but that's because it's Japan. No, if they turned off the magnets, it would the train would not the train would fall, I would imagine, because it's levitating. The train's basically levitating, right? But yeah, sorry, we got carried away in that. But another one is the gravitational field. You can Yeah, you could say, what about hoverboards? Hoverboards are used through wheels. Um, yeah, so hoverboards are hoverboards are kind of conceptual. I haven't seen a hoverboard that would work on like an actual concrete right now because the hoverboards I'm thinking of are the ones with wheels, right? That move back and forth. But yeah. Um, this is I think Lucas talked about this, but this is the formula for the gravitational field, and G, I forgot what G is. It's a really large constant that is it that the bigger an object is, the strong? Yeah. So you can kind of show that through You can kind of show that through here. Like it takes the both masses, right? So if mass one is bigger, then the gravitational field will be a lot bigger, correct? This is what this formula shows. Oh yeah, oh wait, the gravitational constant is given right here. So G is actually a really small force, which is 6.674 times 10 to the 10 to the negative 11th. I don't fully know how they got this. I'm assuming they did a lot of math and like figured out what the universal constant was, but um, I'm imagining you could use this along to find the gravitational constant of Earth, or not gravitate, the gravitational acceleration of Earth, which is just 10 meters per do some useful math examples, even if it's hard. I'll keep that in mind for next time. But I didn't want to go too in depth with force fields either because I don't want to get people too confused. But I can try next time to get examples up and going. If Gavin, do you think you could figure out, you could put some, no, G is a different term and M sub one equals mass of first object and M2 just equals the mass of the second object, right? So, yeah, mass of the source, mass of this. So these two, and then you take the distance between the center of both masses, right? If you have this, you take this is the distance, right? And then you have what? And then you just square it, r squared, and then you have that, and yeah. Yeah, it's just the gravity between two objects, how they're interacting basically. G is just the gravitational acceleration of how they're acting between each other, right? So if let's say if G is equal to what, zero point 0.5 meters per second squared, then that means that these two objects aren't interacting very much, right? They're kind of far apart. They're pulling each other close, but it's kind of like it's not that much, right? Yeah. Yeah, that's correct. Um, what are some, yeah, we just covered this, right? This is the electromagnetic field, part of the electromagnetic force, and the this is just the electric charge is from uh the force created over the test charge, right? Which is just the charge of an object, or it's just Coulomb's constant times the source charge over the distance between the two charges. This is the complicated stuff last time, but you don't need to worry about knowing any of this. This is just like fun fun facts, right? Uh but yeah, you can think of do you guys know the electromagnetic spectrum? So the electromagnetic spectrum is just a wave of different like this is like talking about um a wave of different wavelengths of. So if you think about it like with X-rays, you know how you guys get X-rays at the hospital? That's using um how that works is basically, oh, I was talking about the math between Gavin, I was talking about the math between the, actually never mind, don't worry about that. I'll talk about that later. But yeah, if you wanna, sorry, I can't delete. Oh, I can only delete from here. Sorry. Um, okay. So when you're looking at the electromagnetic spectrum, this is just like the spectrum of all the wavelengths of like possible light there could be, right? So if you go to the doctor and you're getting an X-ray on your body, let's take Bob. Bob is getting an X-ray in this machine, right? When he goes in this machine, he's being blasted by wave or by light or like in invisible light that's at such a short wavelength that it can go through his body, right? Why is R distance? It's R is distance because it's like you need to know how far two charges are from each other to figure out how they like what the electric charge between them is. Yeah, R is radius, right? So when you're looking at like if you're trying to see how these two interact with each other, you have to use the radius or yeah, you're gonna have to use a radius, or if it's just one particle, then you just have the source charge, right? And this is a pretty complicated stuff. If I could talk about this more in depth the next class. I don't have many materials prepared about this because I don't think we would go um more in depth. But yeah, so even microwaves, right? Microwaves work by blasting your food. Sorry, I'm all over the place. Let me finish my X-ray example. Um, so basically, let's say Bob is in an X-ray machine, right? They're gonna put him in the X-ray machine and he's gonna be blasted with light, invisible light that will pass through his body and be sent back out, right? It'll kind of reflect off of him, right? Because it'll go through his skin, but it can't go through his bones. So when it does that, the doctors can see a clear picture of where his bones are, right? So let's say if there's a crack in like if Bob breaks a bone, right? There'll be a little crack in the body and X-ray can be able to go through that. And then it'll show a tiny crack and then back in the report, it'll show the doctors, oh, here's a crack, and we could use x-rays to prove that, right? So it's all pretty that's how x-rays basically work. And the reason why you don't want to get too many x-rays is because it's a shorter length than visible light, right? And anything shorter length than visible light means it's dangerous for us because because it can go through our bodies, right? And it causes radiation. And basically, this means that X-rays, not blue light. Blue light's just a really high, like blue light's a high wavelength of visible light. So it's like that's like blue light's considered bad because it's a higher wavelength and it can technically harm you, but it's um it's not inherently like too bad. But if you go to ultraviolet rays or like X-rays or gamma rays, these are like the really high wavelengths. So these can penetrate your body and cause a lot of harm because that's why when you do X-rays, they use it in moderation. And yeah, so what ends up happening is there's actually like I'm pretty sure there's like policies where you can't have x-rays, like you can't have a certain amount of x-rays or you can't be exposed to it or something like that. I don't know the correct policy, but it's pretty dangerous, right? But microwaves on the other hand, they're very safe, right? Because they have a longer wavelength, so they can't like go through us. That's why we can use can getting too exposed cause our internal. This is it doesn't have to do with internal magnets, it's more with like radiation. Like the radiation kind of like disrupts our body and like it kind of like it can cause cancer, it can cause a lot of bad stuff, right? So that can harm our body. I don't have like necessarily examples of what, but yeah, that's why and that out in the sun is bad because it can cause a lot of skin cancer because being exposed to that ultraviolet light that a lot of it does get blocked, but like a lot of the bad ultraviolet light does get blocked by our atmosphere, but some of it passes through and that's why we use sunscreen to block it off of our skin, right? Um how bad the sun isn't inherently like that's what SPF does, right? SPF protects against most of the radiation, but like it can still like that's how it can still pass through. It's just it's a very low chance, right? That's why whenever it's sunny outside, there's like a UV index, right? It's the UV index on the weather app goes 1 through 10, 10 being the highest, right? If whenever I'm going outside in the summer, I'm looking at the UV index. If it's like above or 3 or something, I'll put sunscreen on, right? Because it's sunny outside. I don't want to get cancer due to the UV lights that could go through me, right? So that's considered higher wavelength. But if we go to down to microwave, right? The SPF has like I'm assuming it has a material that just doesn't allow the ultraviolet lights to pass through our skin, right? There's like special like materials that wavelengths of like wavelengths of light can't get through even if they're um like even if they're high, right? That's what all these materials do. I don't know exactly what it is, but there's something in there. And to measure that, they use SPF. Going down to the lower spectrum, right? If you have a microwave or like a radio, you guys know radio waves. That's what does like all the radio in your guys' car, right? It's very safe and you can use that like to like communicate or whatever because it can't go through a body. And also like it's just great because it helps communicate, right? Like that's like a myth. I feel like it's like I don't want to give you guys the wrong information, but being next to a microwave is not bad because it's a lower wavelength, and what can happen or what happens is that like it's only within this microwave, right? This microwave is very well sealed, and what happens is there's food on this microwave, right? And long-term contact with lower wavelengths is not bad, right? Because like I could like if you look at an infrared, there's infrared guns out there that like measure your heat and everything, right? That can like see how your temperature is. Like that's not bad for you, right? It's completely fine. So I don't know if being in it for long term is even bad, but um microwaves basically just blast the food with microwaves, right? That's what they're called. They just blast the food with microwaves to heat it up, right? And basically when they do that, this food just gets like the all the molecules in this food just um bounce off each other faster and faster until it heats up to the desired temperature you want, right? And then it gets cooler again once it's outside. That's why you can have microwaves in your household, right? Like if it was dangerous for you, I don't think they wouldn't allow us to have microwaves as a kitchen kitchen object, right? You don't see X-rays handled by any of you guys. It's like only in labs, ultraviolet lights, also gamma rays. Gamma rays is the most dangerous, but all of the higher ones are all dangerous, and they're all like all that. Mhm. So something that's dry won't get as warm as a glass of water. Um, it depends. It depends on what the how long like because like food is like something that's dry like a glass like even the glass that's surrounding that water actually can get well hotter than the water sometimes, right? It just depends. A lot of stuff can get hot because the microwaves are able to go through that, right? But it just yeah, I can't go too much in depth because I'm not an expert in the electromagnetic spectrum, but I'm trying my best to answer the I don't know if we'll finish the lesson either. Um, I think we can get through it. We talked about the magnetic field. Oh, this is a really good picture. I didn't know we had this, but the unit for that is Tesla. Um, like it's a simpler version than the electromagnetic field. Yeah, I think we don't need to talk about this. Compasses work off using the yeah. Compasses work. I just like to think of like real world examples for each slide. I don't know why, but compasses work off using the magnetic field. Earth as a whole generates a magnetic field through the poles because there's a ball. The outer core has liquid iron or liquid metal, right? And iron generates a magnetic field, and this magnetic field comes out through the poles, right? And so when you're using a compass and it's like telling you what north is, that's because the one side is getting repelled from that north, and so then the south is like the other side of the magnet is getting attracted, so it'll point this way to north, right? And that's why if you're close to another magnetic thing like in your house, that's why compasses don't work because what ends up happening is metal gets in the way. Yeah, I don't want to. I don't want to spend more time on that. But if you guys have any questions, I think Gavin can ask, or get sorry, Gavin can answer. Yeah. So if it's next to it'll work. I don't know if it depends on how good your compass is. If you have a cheap compass, if you have a cheap compass, end up happening is it'll point to your fridge instead of north, right? But if you have a really good compass, I don't think your fridge will be able to be strong enough to like it won't be strong enough to displace the magnet inside the compass. It just depends on how good your compass is. Um, okay, I was just gonna review tension and compression. I know you guys did this with Lucas, but we're gonna be talking about Atwood machines a lot. And Atwood machines are kind of like a really big part of physics as like mechanical physics as a whole, right? Whenever you're thinking of physics, you're thinking of kinematics, Atwood machines, springs, right? And today we're gonna be talking about the Atwood machines. And Atwood machines are personally not my favorite because they're really hard to deal with. But we'll get through it. I think some of you might find it fun. I personally don't like Atwood machines, but yeah, yeah, they're attracted to Earth's north and south poles, but or like the currents that are created by the north and south poles, right? Um, sorry. I know a lot of you guys kind of did this, but I'll go over it again because this is very important, right? And one of the most important things to know is F equals mass times acceleration. I know I've said this a lot before, but this is the one of the most important things when you're dealing with tension and whatever, right? So when you're thinking of the net force, you also use this. This is, I can't draw it. Sorry. It's called summation, right? The summation or the net force is equal to mass times acceleration, right? And tension is basically just opposing that, right? So if you think of this, if you think of an object hanging with a string off a wall, right? You're thinking of two forces, right? There's a downward force of yeah, it's sigma. It's also called notation or summation. It's just like the total. Don't if you look at this, just think of total, right? This just equals total. You don't have to think about it too deeply. It's just a really cool symbol. This is confusing. Okay, let me get to explaining, Gavin. So basically, let me let me break it down. Let me break this down, right? Let's start from the beginning. So we're given, I'm gonna give you force is equal to mass. Yeah. So sigma is just basically the sum of all forces or sum of all things. Yeah. Mass times acceleration. Correct? Acceleration. We are given this, okay? Force is equal to mass. We can solve how to get to some other day, but for right now I'm just gonna give you force is equal to mass times acceleration, right? This makes sense? And when we're thinking about a hanging object, there's two forces being applied. Technically two forces, right? There's a downwards force and there's an upwards force, right? The downwards force is going to be how much this mass weighs times gravity, right? Because gravity is technically an acceleration, right? So when you think about that, right? And then since this object is staying in this position, this string is also exerting it the same amount of force upwards to keep it up there, right? This force is going to also be m times g, but upwards, correct? Um, if you guys gonna private message me, could you guys private message me on like The name one, because like the one that says my name and not on the iPad, because I'm not gonna look at my iPad private messages. Yeah, the reason it's hanging is because this, if you think about a normal box, right? It's just gonna hang in the air because the mass times gravity downwards is equal to the mass times gravity upwards, right? If the downwards force was greater, then this box would just fall down, right? But we're saying this box is gonna stay in the air. So this upwards is equal to the downwards, right? And this upwards one is called the tension, right? This tension in the string is is tension, right? And technically this tension is equal to the downwards force, right? Tension's also technically a force, and then there's a downwards force of mg as well, right? So in this case, the tension is equal to mg as well, but just in the opposite direction. Can I move on, or is there something you guys have a question about here? Gavin, can you answer the questions in chat? Like, for because I'm gonna be um sorry. So mass and gravity are acting to keep them hanging in balance. What would higher if the upward mg is? It's not pot. Like it won't like if it was higher, then it would just move upwards, right? If you think about it, like if you have this object and it's somehow going upwards, then the box is just gonna move upwards, correct? If but there's it looks like a T too. But yeah, but let's say the downwards force is greater than the tension up being applied, then it'll just move downwards. Right now, I'm just saying this box is hanging, right? The box is hanging and it's not moving up or down, it's just hanging in the position, right? So in that case, the force downwards is just equal to the force upwards because they cancel out, right? So the total net force is just zero. There's two forces being applied, but the total combined is zero. Does that make sense? F net equals zero, but two forces, forces, tension and gravity, gravitational force. Does this make more sense to you guys? Is there anywhere you guys are getting stuck? Because this is important. This is important. This is going to be used a lot today. A lot, a lot, a lot. So when we're technically F net is just the net force, like the net outcome, right? The net I said in the beginning of like the problem, like this box is not gonna move. So that means like the net force is zero on this object, right? The net force. There's two forces, tension and gravitational force, but the total combined just equals out to zero. Um, so a way we can write the F net, right? The net force is just equal to tension minus mg, right? Which is we proved is zero because since this box isn't moving, this tension, or actually no, sorry, I shouldn't say that. Um, usually, usually you'll have it like this, right? Equals ma, right? Because we know the net force is equal to mass times acceleration, right? And tension minus mass times gravity is also equal to the net force, right? So we just do, if let's do this, net equals ma, but F net in this case also equals T minus mg. So what we can do is we can substitute F net for this and then have just T minus mg equals ma, right? And in this case, I've said that this box is standing still, so there's no acceleration technically. So if there's zero acceleration, then this whole thing just becomes zero, so the tension is just equal to mg. Make sense? No, that's fine. Fnet is just so in physics you'll see Fnet a lot. Fnet is just equal to the net force. Net force. And net just means the total force, basically. So when I tell you find the net force, you're just gonna find the total amount of force being acted on the object. And in this case, there's zero net force because tension and mg just cancel out. And since the body is staying still, that's just zero. It's like sigma. It's like the summation. Does this make sense before I move on? Yeah. Yep, yep. Um, so like F net is not the same thing as force because when I want you guys to think of force as like individual forces, right? So like each thing has its own individual force, right? There's a force downwards, there's a force upwards. But when I say F net, I'm just gonna combine all those forces, right? Okay, I can delete this mess. I'm gonna delete it. Okay. Um, okay, yeah. Oh, I like this picture. I should have used this picture earlier. Shoot. Whatever. So if you look at this, right, there's a tension for, I like this. Tension force is just equal to, I'm gonna use P for tension force, and then there's a force of gravity downwards, mg, right? Since, and if we're trying to figure out if what the tension force is, we just have, um, or like in this case, let's say I don't say anything about, um, let's say I don't say anything about the if whether it's like still or it's moving, if it's going down or up. So in that case, we just say the net force is still gonna be T minus mg. You can do mg minus T. It doesn't really matter because what matters is the acceleration, right? Equals mass times acceleration. Um, because what I'm trying to get at is this is basically telling us how this object moves, right? This mass times acceleration tells us if this mass is moving downwards or upwards, right? So if I say like downwards is negative in this case, and let's say it gives us that this block is moving downwards, that means mass times gravity is going to be greater than the tension. Because if it's going downwards, that means gravity is playing a stronger force and the tension is upwards, correct? Does that make sense? Yeah, we're good. All right. Good. Oh, do you want to cover compression? I don't know if I want to cover compression. Uh, I don't know why this is a slide. I don't know if we'll do a book it at the end if we have. So basically, T minus mg and mg minus, yeah, I'm gonna skip this slide, but mg minus t is like the same thing. But when I do t minus mg, it just matters on the outcome, right? So if I'm stating t minus mg and I'm taking um wait. Yeah, if I'm doing T minus mg, I'm taking the fact that this tension is going to be playing a bigger role than mass times gravity because I'm hoping for a non-negative acceleration, right? But if I do mg minus t, I'm stating that mass times gravity is playing a greater role or playing a bigger force than tension. It's like I don't want to confuse you with that because it doesn't matter which way we do it, but it matters when it comes to like systems that are related. But I don't want to go too much into that. Um, oh my God. You guys know what compression is. Basically, compression just like you're compressing an object, applies this equals equal force. I don't want to deal with this. Yeah. Oh, you guys did this last. Yeah, I know you guys did this last time. I just wanted to cover the tension part because that's important. I'm gonna skip that. Okay, this is a fun one. Ooh. Do you guys want to solve this on your own, or do you guys want me to go through it with you? How about this? I'll give you guys the 2 minutes. I'll give you guys 1 minute. I'll give you guys a minute to, sorry. I give you guys a minute to do this problem real quick, and then I'll go through it. Just so you guys can look at it, just so you guys can soak it in before I go through it. Oh yeah, and I'm gonna say sorry. Just assume mass one is bigger than mass two. No, we did not talk about Atwood machines uh last time, Aaron. All right, I'm gonna go through it. I'm gonna go through it. It's always confusing to do these type of problems. So if we're assuming mass one is greater than mass two, we're gonna use variables. I know it'll be hard for right now, but we're gonna put these all in terms of variables. So we're gonna figure out how fast, so a lot of you guys like know that it's probably gonna go this way because mass one is bigger, but let's try to describe acceleration with variables. This is like the really hard part of physics because we're not gonna be using numbers, but we'll be using a lot of um, physics. And this is like the epitome of physics, right? When you think of physics problems, you're gonna be solving with variables a lot of the time, right? So if we're thinking mass one is bigger than mass two, we can automatically assume that this is gonna be going downwards, right? So if it's gonna be going downwards, remember we talked about how if this is going downwards, then we can just say, yeah, let's keep it like this actually. Um, Let's remember we did tension minus m. I'm gonna say m sub one, right? This is the first equals m um sub one a, correct? And this a is wait, is that correct? Yeah, that's correct. Yeah. And since it's going downwards, this a is gonna be negative, right? A is going to be negative in this case because it's going downwards. So we're gonna do negative um m sub one a. I'm gonna stop here. Is there any questions right now on any of like the things? You guys because this I'm gonna do this like slowly with you guys, right? Oh, um I should probably state F. So we're trying to find so we know the F of this mass is equal to negative m1a, right? Because it's going downwards. So, but we also know that the total force of both of that negative m sub 1a is also equal to tension minus the gravitational force of the first one, correct? Does that make sense? And then the second step we're going to do is we're going to figure out this. So we know that this is going upwards and we're taking upwards as positive, correct? So which step do you not get, Sanchana? Step one. Okay, basically we know that there's two forces, right? It's low-key pretty difficult. Okay, we know that there's two forces, right? There's tension acting up on the object and there's mass times gravity acting down on the object, right? That's we can clear that up, right? You guys are gonna be verbal with me if you guys are confused, okay? We can get that part, correct? That there's two forces acting on mass one. But we also know that this mass is going downwards, correct? So this means that mass or the acceleration of this object is going down or is going to be negative because that's what we defined the acceleration as, right? Downwards means negative in this case. I'm going to downward, sorry. Oh, that. Downwards equals negative. That's why we have a negative mass one times g, right? Because gravity is acting downward. Oh, you just said that in chat, Sunshine. Yeah, but that's why we're doing minus mass times mass one, so mass one times gravity, right? Because gravity is acting downwards. So if we have that as a case, and this acceleration is downwards, you have P minus M1G, right? Because we're trying to figure out the total force, right? So when you're trying to figure out a sum of two things, right, you're going to add them together. Like if you're trying to figure out the total of one plus two, one, sorry. Yeah, it's negative M1A because it's going downwards, right? Let's say you're trying to figure out the total of two numbers, right? One and two, and you want to figure out the total. What you're going to do is you're going to add them, correct? You're going to add one and two together. Add one and two together to get three, correct? That's pretty much what we're doing, but with variables, right? We have two forces that we talked about, one going upwards and one going downwards, right? We have T going upwards, this is positive T, and we have um mass times gravity going downwards because mass times gravity is a force, and since G is it's like adding two numbers, right? One and negative two. When you add them up, you're just going to do one minus two, correct? It's the same thing here. So we know this is equal to the total force. Does that make sense? You're making one plus two and one minus two sound so it's basically one plus two and one minus two, just like with variables instead, if you think about it, right? So when you're doing it like that's why I want you guys to think logically about it, right? When you're adding, yeah, like I'm basically saying one is equal to tension and like negative two is equal to mass times gravity, right? And you can basically, if you guys are confused why I'm doing mass times gravity, it's because force of the object downwards is going to be mass times gravity because mass remember F equals ma, and a in this case is g. So that's why we're doing that. So you can think of like negative two as mass one times gravity and like one as t, right? So when you're gonna add these two up, you just do one minus two or do t minus m1g because g is acting down. If we were, you know, does that make sense? Oh, My brain is on. You guys are funny. Acceleration is gravity in this situation. Yeah, yeah. But so do you guys get the first step now? Does this make a bit more sense? The first, oh, did I move to the second? Oopsie poopsie. Does this make more sense, the first step? Um, yeah. Can I get like a thumbs up or something so I like know before I move on? Yeah, yeah, yeah. Okay. I'm gonna move on then. I don't wanna like waste too much time. But okay, since if you guys get what happens with the first one, it's basically the second or the same thing, but with the second one, and the second one's going upwards, right? We're still gonna do t minus this time it's gonna be m2 because we're taking the mass, right? T is since we're taking up as positive, and since it's going, and we're just gonna do m2a because the acceleration is upwards for this one, right? It's not negative, it's upwards, correct? And notice the acceleration. And notice the accelerate. Okay, you guys only need to like kind of get it. Like physics, if you just kind of get it, it's like you're never gonna fully get how to do physics. Like, I fully don't know how to do physics either, right? Like I'm what you call a LARPer, correct? Um, um I teach what I know, and so uh so do you guys get how I what I got for the second equation? I agree. Gavin's a bigger LARPer than I am, but do you guys get what I did for the second one as well? T, but this time the acceleration is the same, right? If you think about it logically, right? What does the two equations? Because we're trying to solve for acceleration, correct? We're just trying to solve for the acceleration, and notice that the acceleration is the same because if you move I don't have a string on me. But oh, I could okay. Let's do this. Let's do this, right? Let's say I have this, right? And let's say this string moves downwards by some amount. This string will move upwards by the same amount, and it'll move at the same speed, right? It's just going the opposite direction. That's why the acceleration of both objects will be the same. It's just in different directions. So when we're solving, now it's the easy part. We just solve for A in terms of the masses and gravity. Why is subtracting the M2G as well? Um, like since China, since gravity's always going downwards, right? So we're just gonna be subtracting, but the acceleration is going upwards. This is why this is positive and this is negative, right? There's still going to be a gravity acting downwards on it. It's just going to go up, and the result of it going up is positive, correct? Does that make sense? Yeah, yeah, yeah. So, we can take out t, right? We don't need to know t. We'll just sub out t. Yeah, let's just do t equals what? M2G plus M2A. So gravity is pulling it down, but tension is pulling it up. Does that make sense? Yeah. Okay. So tension is equal to I just added M2G on both sides. We have to solve for A still. We just got the base on, and now it's the easy part. Since we got both the equations, we can just solve for A. Let's add M2G to both sides. You get T is equal to M2G plus M2A. And then you can just substitute T in the first equation with um, M2G plus M2A. So you just get M2G plus M2A minus M1G equals to negative m1a. Correct? Does this make sense how I just substituted t? I just solved for t and then substituted with this over here. Does that make sense? Yeah, a is acceleration. Okay, okay, okay. I'm gonna erase everything on the board, but can I erase everything and I'll just rewrite the first two steps, correct? Can I do that? Okay, I'm gonna because you guys get how to do sorry, it's negative a. Negative m1a. Step two, it's the same thing. M2g equals m2a, right? And now we just have three. We're gonna solve for this t by adding m2g on each side, right? If we just add this, because we're trying to get rid of t. We're just trying to solve in terms of g and the both masses, correct? Does the step three make sense? Does step three make sense? What I did, I just added both m2g on both sides of equation two, right? Can I get a yes or no or maybe or kinda no and anything? Thanks, Gavin. Maybe. Um, like you could also like okay, let's focus because I like I need a lock or we need a lock in. Okay, yeah, Sanchana, we're getting somewhere. Yes, that's technically correct. But I'm trying to get through step three first. Does everyone get step three? I mean, if you want to get the question right, technically you could, yeah. I mean, if you get good enough at it, you can just do it in your head, but you want to write it down. You want to write it down. So then step four, let's just substitute this in here. So you get m2g plus m2a minus m1g equals negative m1a, correct? Right. And since we're solving for a, let's get like anything with a on one side. So let's get it here, right? So if we have step five, we're just gonna have m2g plus or sorry, minus m1g equals m2a minus m1a, correct? This makes sense, right? Valid, valid. Did I do something wrong here? Ugh, there's no way I did something wrong. Oh, it's minus. Oh, sorry. Okay, that's what I missed. Sorry, guys. How'd you guys not catch that? It's negative M2A, right? Gosh, guys. That's not my fault. You guys should have fully caught that. Um, right. Does this make sense? Does step five make sense? Negative M2. Yeah, I was testing you guys. You guys failed. God. Hey, wait. Am I think I am doing this right. I don't see why I would not be doing this right. Yeah. Negative -2 plus minus the -3 is the okay. You got lost a while ago. Um, I didn't mix it up, did I? Okay, wait. I swear I did this right. I swear I did this right. Ah, I think I did. Wait. Okay, so let's just let's let's flip it. Let's do M1A equals M1G minus M2G, correct? This makes sense, right? I just added in the minus on each side. I just flipped it so it's just the A's are positive and this is negative or like, are we following? And now we can just factor out the A. This is what physics is, guys. Just learning how to guess and check and make sure you're not doing anything wrong, right? And then you just have G M1 minus M2 over. Is this what you got, Evan? Yeah, I think this is what Evan got. Equals. Okay, yeah, I'm gonna re-explain it. I'm gonna re-explain it. I just need to make sure I solved it for myself because it'd be quite embarrassing if I didn't if I did get a different answer. Oh my God. Okay. Let me just write the answer down so I don't waste your guys' time again. M1 minus M2 over M1 plus M2. Wow. Oh, that's so rewarding. Okay. Okay. Now I'll go back to step five and explain it. So, you got last at step one and two. Um, Gavin, do you think you could explain step one and two? Yeah, Evan like solved it like 10 minutes ago, but Gavin, can you
Wait, yeah,
Gavin, can you explain um
yeah.
the can you explain the first steps?
Um,
Or not like in chat. Don't do it
okay,
on call
okay.
because you're a LARPer. But
Okay,
just
wait,
do it
but
in chat.
why don't you just plug in the acceleration formula?
There's no you can't.
How?
Because this is not good. How what tell me what the acceleration formula is.
A equals M1 minus M2 over M1 plus M2 times G.
That's what I just solved for, Gavin.
I know. Well, that's the formula.
Yeah, but we're trying to solve for the formula. Okay,
Why do
okay,
you
I'm gonna
solve for the
explain this
formula when you
problem.
could just plug in the formula?
But you have to learn where the formula comes
Okay,
from.
okay, bro.
Gosh.
People
Okay.
don't learn where.
Um,
Okay, whatever.
okay, I'm gonna quickly explain this problem and then we can do a block it, okay? Because Gavin just explain steps one and two from chat, but basically in step five, I just wanted to make a positive, so I just added a to each side, and then I just minus M2G and then added M1G, so I just flipped it, right? The step, and then once I did that, you can like if you guys know factoring, M2A plus M1A is just the same thing as saying A. This is complicated stuff, but as this is the same thing as this because when I distribute this A back, it becomes the same exact equation, correct? So it's just the same thing. I just backed it out so I could just get A alone because we're trying to solve for A, correct? And you can do the same thing to the other side because it's just M1G minus M2G, correct? So then you can just factor out the G. I know. This is a lot of focusing to do, but I'm almost done, promise. The board is too crowded. Okay, do you guys know how to factor? Do you guys know how to factor? That's basically what I did. I just basically um M2G minus M1G. If you guys are willing, um, is it fine if we go a bit overtime so we can do the booklet or no? Are you guys fine with that if we go a bit overtime to also keep the booklet running? Um, so M2G, M1G, M negative. Oh my Lord. Okay. Hey, it's good that you guys are even like learning. Like, um, so basically, I think right now, you guys can kind of like, um, you guys can kind of like, I don't want to say memorize because that's a bad teacher. Like, that's a bad thing to do. But right now, you can just take these as a given, right? Just take these as a given because it'll help you learn the rest of the steps, okay? So just take steps one and two as a given. You have none? If you don't have notes, you can just screenshot my board. I'll also post the slides and the thing, but um yeah, just screenshot my board as well. So screenshotting my board is probably the best thing you could do if you didn't write down notes. But if you guys get to this step, you can just factor out the G's from both sides. So just get G M2 minus M1 equals A times M2 minus plus M1. Yeah, and then you could divide each side by M2 plus M1 to cancel these and then have A alone. Wow. Oh my God. Oh yeah, wait, I'll also have the video up. I forgot. I'm recording. So I'll have a video up as well. So if you guys want to go back and watch the video, go ahead. Feel free to. If you guys are that dedicated to learn. Oh my God, Gavin doesn't even know what he's doing. Okay, you can read his chat. I don't know if it'll help you guys, but what booklet should we do? What do we cover? Can I delete my annotations? It's something that require no like give me your favorite physics topic in everything you guys have learned. I'll take a poll and then I'll um Gavin, shut up. I don't like classic. Right. Um energy. Ooh, we didn't do it. We haven't done an energy block yet, right? Let's do energy block it. Yeah, let's do an energy block it. Projectile Evan, there's no topology. There's like I don't even know topology. Wait, Evan, what grade are you in? Okay, yeah, okay. He's LARPing. He does not know topology. He okay. I if he knew topology, he would not be in this class. Okay. You're not I'm not gonna feed into this LARP. Okay, he's LARPing. He's LARPing. You can't tell me the first thing about topology. There's no way okay, okay. You know little. Um, let's run a Oh, I'll stop sharing real quick and then we'll run book it. Okay, do you know what the donut's called? There's a name for the donut.
Dr. Donuts.
No, don't. Oh my God. Yeah, you don't want to aim for the donut. He's LARPing, guys. Slime him out. He's LARPing.
Yo, chill on.
LARP,
Yo, chill on him, bro.
LARP, LARP, LARP. Sorry, Evan. That was mean. Oh, I should probably end recording.